Hello everyone, welcome back to Networks class. Last time in class, at the beginning of class, we spent a little bit of time talking about looping in GAMs. So you should all be now familiar with how you can solve a sequence of optimization problems that are just slightly different from each other in GAMs. And then we talked about Bender's decomposition for shortest path interdiction. So this came out of the fact that we had this mixed integer program for shortest path interdiction, but we were kind of unhappy with it because we wouldn't get a lot of pruning in terms of branch and bound. And so Bender's decomposition gave us a different way of solving this, which was we had this partial master program and we generated constraints over time to add to the partial master. And at the end of class, we got down to writing that algorithm, but we weren't able to do an example of that. And so next time we come back to this topic, we're going to do an example of Bender's decomposition. But the plan for today is to go over the homework that was due today, which is homework 2 on shortest path modeling, and then to introduce the next homework assignment, which is homework 3.1, which is you can think of homework 3 as basically a practice project that we're all going to do together as a class. So we'll introduce that at the end of class today. But let's begin by going over some of the answers to homework 2. So the first problem in homework 2 was just running Dijkstra's algorithm. So hopefully you're all familiar with how to do that. So the first interesting problem on the homework was maybe homework problem number 2, which was to give a small example of a graph where Dijkstra's algorithm fails to work because there's a negative length edge. And a good example would be something like this. So this is the start node, and here we have two other nodes. And let's say this edge length is 2, and this one is 5, and this one is minus 4. So if you run Dijkstra's algorithm on this graph, what would happen is it would pop off this bottom right node first because it would see this edge of length 2. That would be the smallest number in the queue, and so it would pop this node. And as soon as it pops the node, it fixes the distance to that node. So at that point, the distance to this node would be fixed to 2, and Dijkstra's algorithm doesn't have the chance to see this longer path with more edges, but with a shorter distance. So the problem is here is that this edge makes Dijkstra's algorithm think that routes going this way would be more than 5, but in fact when you add this minus 4 they end up being much shorter, 1. So Dijkstra's algorithm doesn't have the opportunity to take into account this minus 4 into its path calculations, and that's why it doesn't work. Basically it just relies on the fact that if I see this 5, distances or paths that go through here are going to have more than 5 distance, which isn't the case with negative length edges. Now there's other algorithms that do take into account negative length edges, but those algorithms run much slower than Dijkstra's algorithm. And that's because they really have to spend a lot of time to make sure that these long paths don't potentially have a negative length edge that could make the path overall have a short distance. So that's the basic idea about why Dijkstra's algorithm only works if you have non-negative length edges. So then problem 3 asked you the following. So somebody comes along and tells you you can just add a constant to all of these edge lengths to make them positive, and then the algorithm would work. So the idea would be something like this. To just add a 4 to all of these edge lengths, and then all of them would be positive. So this one would be 0, this one would be 9, and this one would be 6 when we add the constant 4 to everybody. But you can see from this example, this would tell us that this is the shortest path from S to the node on the bottom right. But that's not the case because the shortest path was this one originally. So something's going on here. And the basic idea is that since we're adding a constant to all the edges, we're not maintaining the relative order between paths. So here we had 2 paths. So path 1 just went from S directly to this node, so I had a single edge. And path 2 had 2 edges on it, which were these 2 edges. And originally, we had path 1 of length 2, and path 2 had a 5 here and a minus 4 here. But when we add a 4 to each of these edges, it doesn't maintain the relative order between these paths. So when we add a 4 to this path overall, we would have added only 4 because it had one edge. But to this path down here, we would have actually added 8 because we're adding a 4 to each of its edges. And so that's what happened here, which is why we didn't maintain the relative order between these two paths in terms of which one is better. So that's why just adding a constant to all the edges doesn't work, because adding a constant to all the edges actually changes which path looks better, because we're adding more to some paths and less to others depending on how many edges that path has. So that's the basic idea for number 3. So let's talk about number 4. So number 4 was this question about routing a ship, and you have kind of a changing forecast and you want to get the ship to port. So kind of a first crack at solving this problem would involve creating a network that looks something like this. So you just grid up the ocean, and the ship is right here, and the port is right here. And you might have edges going between these squares, and sort of the cost of the edge depends on the forecast. But the problem with this is that this doesn't take into account a changing forecast. So we need to somehow take into account that these costs might change over time. So the basic modeling technique of doing that is the following. So instead of having just the grid be all of our nodes, what we're going to do is we're going to take that grid and just lay it on its side. So you can imagine that these are all the grid squares here. And so here's another version of the grid laid down on its side. And maybe we do it again over here. And let's just do it one more time. So the basic idea for this is that now a node is not only a location, but it's a location at a particular time. So these nodes down here mean that you're at this location 0 minutes, at 0 minutes. Over here, it would mean that you're at this location at 15 minutes. Here would be at that particular location at 30 minutes, and here would be at 40 minutes. So now the ship, of course, starts in a particular location at 0 minutes. But the port actually has the same location at all of these in all of these grids. So here's the port again, the port again on this square, and then the port again in this square. So now when a ship decides to, let's say, move to the east, that's going to take it 15 minutes to do so. And so instead of putting the edge between these two nodes, what we're going to do is put them between these two nodes. So this signifies the fact that it took the ship 15 minutes to move from this location to this location. And it might take it 15 minutes to move north as well. Or it might even have the option of staying in the same location. So those are the 3 things that maybe the ship could do from its current position, is move east, north, or stay in the same location. And similarly, let's say it were in this location in 15 minutes, it could move east, or north, etc. So the idea now is that when a ship takes an edge, it not only moves it in terms of space, but it also moves it in terms of time. And of course, the costs on these edges are going to be dependent on the forecast. So costs depend on the forecast. And of course, if I have one forecast for the first 15 minutes and a different forecast for the next 15 minutes, these costs are going to be different, kind of depending on the forecast for that particular time period. And so if I have a forecast that's changing every hour, you could imagine that I have lots of these grids up here. And so for the first hour, I have one set of costs. And for the next hour up here, I would have a different set of costs than we had for the first hour here. So that's the basic idea of setting up the network. But now let's think about a shortest path here. So we'd like to solve for the ship starting in its current location. And we'd like to get it to port, but using the minimum amount of fuel. So we have a clear starting point because at time 0, the ship is in this location. But let's think about what should be the ending point of the shortest path. So if we say that the ending point is this node right here, what we would be saying is that the ship has to get to port at 15 minutes. But we want to give the ship some leeway as to where it gets to port. So we want to say you can get there at 15, you can get there at 30, you can get there at 40, basically whatever time that you want. And to do that, we're basically we're going to create a fake port node. So this is some kind of fake node, an end port. And we can connect all of these port nodes with that end port. And let's say we give all of these a cost of 0. So if we do that, we're basically giving the shortest path an option about when it gets to port. So it's just as good to get there at 15 minutes as it is at 30, as it is at 40, and so forth. So the shortest path can choose. And you can do a bunch of things with these edges to kind of create some real world constraints. So suppose that we have to get the ship there within the first 2 hours. It's no good to get there after the first 2 hours, but we want to use the minimum fuel as long as you get there within the first 2 hours. Well, the way you can do that is basically only put edges here for the time layers that correspond to the first 2 hours. And then don't put any edges for the time layers after that. So that would make sure that if the ship gets to end port, it can only do so in the first 2 hours and not afterwards. Another thing that we could do is kind of put some penalties for getting there later and later. So maybe there's no penalty for getting there at 0 minutes, no penalty in 15 minutes or 30, but maybe after that, we want to put some amount of penalty for getting there later and later. So here, maybe there's a cost of 1 associated with this edge. So this means that essentially being late 15 minutes here, so arriving at 45 instead of at 30, we're going to say that that's equivalent to 1 unit of fuel. And so we're giving the option to the shortest path. Yeah, you can be slightly late. We're going to penalize you for it. But as long as you save more than 1 unit of fuel, we're still going to be happier being slightly late than being at this time. And of course, you can have these penalties get bigger and bigger for these later and later time layers, which would penalize you more and more for being more and more late. And so that way, we're still kind of giving the ship some leeway as to when it gets to port, but we're making sure that it gets there reasonably quickly as opposed to waiting forever so that it gets the right conditions to get the minimum amount of fuel. So that's the basic modeling idea for number 4. And there's really two things to learn out of here. So the first thing is this concept of time layering. So the idea here is that quite often in networks, if we want to incorporate the concept of time, what we're going to do is we'll just take our network and replicate it once for each time period. And now things that consume some amount of time are going to be edges between these time layers. And so I want to point out that right here, the options that we have is sort of move one grid square, and these, based on the problem statement, take 15 minutes. But I could potentially have an action that maybe takes 30 minutes instead of 15 minutes. And if it takes 30 minutes instead of 15 minutes, it's perfectly fine to have an edge that kind of misses one layer. So this edge right here corresponds to an action that takes 30 minutes instead of an action that just takes 15 minutes. So the other thing I want to point out is you can think of this time layering and these edges as kind of the same model as the 15 puzzle. So over here, the state of the ship is a location and a time period. And these edges represent actions that the ship can take, like move north, move east, etc. And each action has associated with it a cost. And we're just trying to find the minimum cost that the ship can incur to get to its desired location, which is the port over here. So time layering is the first modeling concept to learn out of problem 4. And the second modeling concept is this idea of introducing some kind of fake nodes. So we introduced this endport fake node. So it doesn't have to do with a real location in terms of the real world. But its purpose is to kind of give the shortest path a choice about at which time period it gets to the port. And so oftentimes introducing these fake nodes can be quite useful in modeling some real world situations. And by the way, in terms of problem 4 and its realisticness, a routing system using this concept has actually been implemented for the Navy by people at NPS. So this really is quite a real world application. Of course, if you did this in the real world, you would be much more careful about exactly how these things get implemented, exactly what costs you put on the edges, etc. You might not want to grid the ocean with grids. You might want to use hexagonal grids because that makes different centers be equidistant from each other. Another thing that you might need to incorporate in a real-world system is the fact that the forecast is getting updated over time. So we might have one kind of prediction right now, but as we are sort of moving the ship along here, an hour later we might get an update on the predictions. And then what you would need to do is kind of, once you're here, resolve the problem with the new best information that you have, which might change your route slightly on how you get to port. But at each point, you would be sort of routing yourself with the best information that you have available at the time. So that's the basic idea for modeling for number 4, the ship routing problem. So let's take a look at the next problem here, which is number 5, which was Beverly owns this vacation home, and she has these bids of various people wanting to rent out the vacation home, and we want to help her get the maximum amount of money out of her vacation home. So the idea here is that each node would be a day. So this would be something like day 1, day 2, day 3, etc. And then if I have a bid for starting at day A, ending at day B, and the bid is of a cost C, what I would do is I would add an edge from A to B, and I would make its cost minus C because Beverly wants to get the maximum amount of revenue, and if we're going to solve a shortest path, we want this to be minus C. But besides adding these edges, you also have to add some zero cost edges between the days. So these zero cost edges correspond to the important option that Beverly actually takes no bid. And the reason for that is that there might be some bid here worth $1 million. And so we want to give Beverly the option of not taking any bids up here, coming in, taking this $1 million bid, and then taking no bids afterwards. So that's the basic idea of Beverly and maximizing her revenue. And by the way, you can think of Beverly maximizing her revenue in much the same way as we thought about the ship problem. So here, a state would be a particular day, and these edges coming out of the day are the options that Beverly has for that day. So she could take this bid, or she could take no bid at that point, which corresponds to this zero edge. So very similar in terms of interpretation as to what the nodes and the edges might mean in terms of states and actions. So that's number 5, the Beverly problem. So let's talk about number 6. And this was the problem of personnel planning. So we have this construction site, and we have various numbers of workers that we require the various months. So in particular, in February, we will start with 3 workers. And in March, we might have 1, 2, 3, 4, 5, 6, and maybe so forth workers. In April, we also might have 1, 2, 3, 4, 5, 6, and maybe so forth workers, etc. And then at the end here is August, where we might have some numbers of workers. And then in September, we were told that we have to end with 3 workers. So the idea here is that these are going to be our nodes, and the edges here correspond to the various actions that we have available. So the costs here are determined by the rules of transferring workers in and out of the site, and the penalties for being under the target. So for example, in March, we had a target of 4 workers. And so if we're actually at 2 workers, we would incur that 200 times 2 penalty for being at 2. So that would get incorporated into the cost of this edge right there. And so similarly, we would have edges out here whose costs are determined by these various rules. And so our shortest path would start from February 3rd and end in September 3rd. Well, not February 3rd, but February with 3 workers and end in September with 3 workers, because that's what we were told. But suppose that we just change this problem a little bit, and let's say that we want to allow ourselves to end with any number of workers in September. So I could end it with 3, but I could end with 4 or 5 or 6, etc. So the way that you could model that is, again, by introducing a fake node and adding all of these nodes from September of cost 0 to this end node. So if we do that, we're now giving the algorithm some choice, saying that you can end in September in any node that you want, and just pick the one that is going to correspond to the minimum cost. So one thing I really want to point out is the similarity between this construction worker problem and the ship problem that we had before. So over here, we had the time layers, and then the state of the ship in a particular time was our node. And then the edges here were the various actions that the ship could take. And that's the same thing that's going on over here. So here we have the time layers in terms of the months. And then instead of having the location of the ship, we just have the number of workers on the site. And then these edges are just determined by the various actions we have available in terms of how many workers we can transfer in, how many workers we can transfer out, etc. And even the end node right here, we could model as kind of a fake end node, the same way that we modeled it with a fake port node at the end of the ship problem. So mathematically, this construction worker problem is just very, very similar to the ship routing problem that we had in number 4. But that's the basic idea for number 6 and how you could go about solving number 6. So let's talk about number 7. So number 7 was the safest path problem. So here we have a Pij, that's the probability of getting attacked on edge ij. And what we want is the safest route from 2 points. Let's say the safest route from A to B. So the basic idea here is the following. So we want a path. So let's consider a particular path. And let's write down the probability that we do not get attacked on the path. So that probability would be the product over all edges in the path of the probability that we don't get attacked on that edge. So this is the probability of not getting attacked on path P. And what we'd like is the path that maximizes this probability. So that would be the safest path. So we'd really like to solve this problem. But oftentimes when people are thinking about this, one idea that they have is that this is somehow equivalent to finding the path where you're minimizing the probability of getting attacked. But then what they write is something like this. So the product over all edges in the path of Pij. But I want to point out that this expression right here doesn't actually mean the probability of getting attacked on the path. This is actually the probability of getting attacked on every edge of P. So this is kind of an extreme case where you're getting attacked everywhere. So these two things are not equivalent. But this is actually equivalent to something. It's equivalent to minimizing the probability of getting attacked at least once. And the way that we would write that is something like this. 1 minus the product over all edges in the path. 1 minus Pij. So these two things are actually equivalent. In terms of they'll produce the same path. And the way that you can see that is that, well, this 1 is just a constant, so you can take it out of the optimization operator. And then this minus 1, we can swap it with this optimization operator, and you would just get a max. So you would be back at, so we would have started at this problem, and we would end up with that problem over there. So these two are equivalent. But you have to be careful about exactly what expression you're writing down here. So this is the probability of getting attacked at least once. Okay, so now we have an understanding of the various equivalences between different ways to write down this problem. But let's try to think about how you can actually solve it. So this is the problem that we want to solve. We want to find the path that gives us the biggest safety. But we don't know how to solve a problem like this because we have this kind of product. But we know we can change products to sums if we take logs. But let's understand a little bit about why we're allowed to take logs. The reason we're allowed to take logs is the following. It's basically because log is a monotonically increasing function. So what is a monotonically increasing function? It's just a function that goes up and to the right. So here's one function that's monotonically increasing, and here's log that's monotonically increasing too. But the basic property that monotonically increasing functions have is the following. If I have two numbers a and b here, and I pass them through the function, so this would be f of a here, and this would be f of b over here. Monotonically increasing functions kind of preserve the order between these things. So if f is a monotonically increasing function, then a being less than b implies that f of a is also less than f of b. So they maintain the order. So in terms of optimization, if I'm trying to find the minimum, if I pass everything through a monotonically increasing function, whatever gave me the minimum originally is going to give me the minimum again afterwards. So some things that, some monotonically increasing functions that you're familiar with are things like this. So you know that if a is less than b, then that means that a plus 5 is also less than b plus 5. But this just comes from the fact that that x plus 5 is a monotonically increasing function. Another fact that you're familiar with is that if a is less than b, then 3a is less than 3b. But that's again because 3x is a monotonically increasing function because it has a positive slope. But you know that if this 3 all of a sudden is a minus 3, then this function isn't monotonically increasing, it's monotonically decreasing. And so that's why we can't multiply by a negative number and sort of keep the less than sign pointing the same way, because it doesn't have this monotonically increasing property. So going back to this problem of trying to find the path that gives us the safest route, if I have some kind of path p star that gives us the safest number over here, then the same path is going to maximize the following quantity. So maximum over path, the log of the product over ij in the path 1 minus pij. So here, all we did was we just took this monotonically increasing function and passed all of these quantities through it. And so it's going to maintain the same order. And so whatever path was best here is going to be the best one down here as well. So let's work with this now. We can just apply our log rules. So we know that the log of a product is same as the sum of the logs. So that's just equal to the max over all paths of the sum over ij in the path of the log of 1 minus pij. Okay, so we're getting closer to a shortest path problem here. But let's think about what's stopping us from saying shortest path. So first we have a max, which is bad. But then also, if you think of these as our edge lengths, because that's what we're summing for each of the edges in the path, these numbers right here are negative because this quantity right here is between 0 and 1. And so the log of something between 0 and 1 is negative. And so we have a bunch of negative edge lengths over here. So the way that we're going to solve this is we're just going to take this optimization problem and multiply it by 1. So here it is. We multiplied it by 1. And I'm going to take one of these minus 1s and move it inside the optimization operator. So the other minus 1 stays out here. And then I have a minimum over all paths, the sum over all ij and p, minus log 1 minus pij. So now this number right here is positive. So we're assigning a positive length to each of the edges in the path. And so you can just use an algorithm like Dijkstra's to identify the shortest path. And all this minus 1 is doing out here is making sure that these two numbers are equal. So it's just saying that from the shortest path, you're going to get some number. But if you wanted to solve this original problem, you actually need the negative of that number. So the last thing I want to point out here is that even though we've written this as though we're listing out all the possible paths from A to B, this is not how we're going to solve this, right? Because this is just the shortest path problem. It's just saying, find me the path that has the minimum distance where these positive numbers are the distances on each of the edges. And so that problem we can solve using just our linear programs or Dijkstra's algorithm or something like that. And whatever path comes out of Dijkstra's algorithm is the one that we know we are the safest on. We're going to get a bunch of practice with this problem on the next homework assignment, which is going to really clarify all of the issues here. And you'll be able to compute both the likelihood of getting attacked and the shortest path and the safest path, etc. So we're going to get a lot of practice with that. So that's number 7. And in number 8, I just asked you to create a homework problem. So if you create a particularly good problem, then I might include it on the next test. So hopefully that means some free points to you. So that's kind of concludes our discussion of homework 2. And let's move on to the second topic, which is just introducing the next homework assignment. So the next homework assignment that I'm asking you to do, you can think about it as kind of a practice project that we're all going to do together as a class. So here's the basic setup of the practice project. So there's a drug lord that's in Arizona. So he lives in Flagstaff, Arizona over here. And we're working with the Arizona State Police. And the Arizona State Police has, for months, been building up evidence against this guy. And they're ready to go and raid his offices. But he gets a tip-off that we're raiding his offices. And so now he's on the run. He's trying to make it out of Flagstaff and out of the state of Arizona so that we can't capture him. And our goal is to work with the Arizona State Police to try to capture him. And basically, the tool that we're going to use is that the police could set up various roadblocks on the Arizona highway. So maybe they block this highway, and then that makes it more difficult for him to escape in this direction. So we want to help them figure out where to place these roadblocks. And there could be various real-life constraints on this. So for example, maybe the police doesn't have enough people to block off every highway. Maybe the person who's running away is going to try to run away to Mexico instead of to one of these other U.S. states because maybe he feels safer in Mexico, etc. So we're going to go through all of these kinds of modeling issues in this project. But the very first thing that we have to do is figure out at what level of detail we want to model the real world. And at two extremes, you can think about it. There's two extremes of modeling. On one extreme, we kind of model every detail about the road network of the state. So every little road in every little town, every highway on-ramp and off-ramp, every desert road. So you can think of that as very low-level, fine-grained model. And another kind of model would be very high-level and much more coarse-grained. So here, maybe each city would be a node, and if there's a highway connecting two cities, maybe that would be an edge, etc. And so our job initially is to try to decide at what level of granularity we want to model the real world. And there's really a lot of things to consider here. So let's just discuss about some of the positives and negatives that you have for each kind of model. So one of the things that could happen is in real life, you might have a lot of time pressure to produce an answer. So if you're working with the police, they might need an answer tomorrow because tomorrow they have to set up these roadblocks. And if you have such kind of a time pressure, you might just not have the time to go and collect all of the real world data for every little road in every little town. You might only have the ability to go and search and find a map of the state and then create the network yourself. And if that's happening, then that's probably going to push you to this coarser model as opposed to the fine-grained model. Another thing that could happen is that a coarser model ultimately has less nodes and less edges. And so computationally, it's going to be easier to solve the coarser model than it is to solve the more fine-grained model. So those are some advantages of coarser models. Another advantage of a coarse model is that oftentimes it's easier to understand what the model is doing. So whenever you go and try to apply these models in real life, the first thing you should do when you get an answer out of the model is think about, does this answer actually make sense in terms of the real world? So just because it's coming out of the model doesn't mean that we have to go and use it right away. We have to kind of make sure that it passes some intuitive understanding of why the answer looks the way that it does. And to get that intuitive understanding, we often have to go in and try to understand why the model produced this answer. And if you have some very finely detailed, complicated to understand model, it may be very difficult to know why it produced the answer that it produced. And it may be difficult to guard yourself against bugs in your own model because, the models that we create, there could have been some kind of GAMS programming error or some data error. And if there's a lot of details to it, it might be hard to track one of these down or to even know that one of these is going on. While in a coarse, kind of simpler model, it's easier to track through everything to make sure that we understand why the model is producing a particular answer. So those are various advantages of the coarse-grained models. But some disadvantages of coarse-grained models is, of course, that they don't include all aspects of reality. So for example, if there's some kind of desert road over here, and our model doesn't include this desert road, it's just never going to know that the drug smuggler has the possibility of taking this desert road to get out of the state. And so the answers that we get out are not going to take that in as a possibility. And so quite often when you talk with non-modelers in the real world, the kinds of things that they'll be pushing you to is to include every bit of detail of the real world into your model, because they're going to ask you questions. Well, did you include this road? Well, did you include that road? Well, did you do that? And I think the thing to keep in mind when you're trying to create these models is the following. So first, no model is going to be able to incorporate all aspects of reality. And so in some sense, what we're using our models for is to provide us with some kind of intuition as to what should be the right actions that we should do, and not necessarily as a total predictor of what's going to happen in real life. So that's the first thing. And then the second thing to keep in mind is that the more details you include, the more difficult it is to actually understand what's going on, as we talked about earlier. And so starting simple, making sure that you understand why the model is doing what it's doing, and then adding complexity a little bit at a time is kind of the right way of doing these models. So always start simple and add complexity as you go along. And you'll see that we're going to do that in this homework assignment as well. So for this particular problem, we've decided to model everything like this. So here we have some kind of relatively coarse-grained network. So each city is a node, and highways between cities are edges. And you can see that this isn't totally exact. So for example, this highway I haven't modeled totally correctly. And this edge right here is totally wrong. There's no highway there. It should have probably been across this way, but somehow I made a mistake while drawing it. And so the thing to keep in mind is whether these details actually make a difference to the answer. And we'll see in the course of this homework assignment that there's all kinds of details that really make absolutely no difference to the kind of answer you get at the end. And so we can keep track of this edge right here, and you'll see in about a week whether that particular edge made any difference or not. But at the end, once we actually choose this network, our model only knows this network and doesn't know anything else of reality. So those are the only edges and nodes that it knows about. And so that's the only considerations that it's going to take into account when it's modeling the escape of this drug lord out of Arizona. And of course, we know that the drug lord would prefer to escape to Mexico instead of other U.S. state. And so, anticipating that, we're going to add a couple of fake nodes, one in Mexico and one in another U.S. state. And we're going to connect the various exits out of Arizona to these two respective end nodes. And we're going to create a final fake node that's escape out here. And the drug lord is going to start out in Flagstaff, and he's going to head out to escape. And he can do that either by escaping through another U.S. state or through Mexico. So that's the basic setup of your next homework assignment. Uh, it's not a one-day homework assignment, so please start it sometime soon. It's all about the GAMS modeling and computationally modeling the escapes of this drug lord and the various ways that we can help the Arizona State Police stop his escape. So thanks a lot for listening. That concludes lecture for today, and I'll see you all next time.